Let's see. I'm happy to be interrupted with questions. It's a different matter whether I'll be able to answer them, but I'm happy to be interrupted. Maybe there will be others in the audience who will be able to answer them also. Okay. I don't know how this will work, but this is the way I've arranged it. So it's all written out. So I hope to be able to write something in between, so in order to slow down. So let's ask ourselves, what is an algebraic group? So the short answer is, it's a group object in the category of varieties. Now that may be explaining something that we don't understand in terms of other things that we also don't understand. So, I believe this is a good description. I like this description, and I hope you will like it too. So let's understand what we mean by group object in a category first. So what is a group object? Suppose we have a category, e.g. sets and maps. I mean, category just means you have a bunch of objects and you have a bunch of maps that are allowed between them. And these maps must satisfy, there are certain axioms which are very natural. Very likely you're familiar with them. If you're not familiar with them, they are very, it doesn't really matter so much. So you could have just sets and maps. So here the objects are sets and the morphisms between them are the usual set maps, functions as we know them. Or to give another example, you could have topological spaces. And then when you have topologies on sets, it's natural to look for the map, insist that maps between them be continuous. So here in this category, which I have indicated top, I suppose you can see my cursor, right? Yes. Okay, yes. Good. Yes. Yeah. Okay. So in this top, objects are topological spaces, and the maps or morphisms are continuous maps. Not just any old set maps, but continuous maps. Okay. And the category of interest to us is that of varieties and morphisms. Okay. Now, Krishna has defined affine varieties, affine algebraic varieties. In the very first talk, Christian's talk, they were called just algebraic variety. But if you look at the definition, that corresponds to more precisely affine algebraic varieties and morphisms. This is the category that we are interested in. And I understand that this is an issue at the moment, but eventually we will be working in this category. But one thing you should note about this category, and I'll come to this later again, is that objects here can be thought of as topological spaces and morphisms as continuous maps between them. And obviously, you can forget, if given topological spaces and continuous maps, I can just throw away the topology, throw away the continuity, and just think of topological spaces as sets, and these continuous maps as functions between sets. So there is a hierarchy. In other words, I can look at an variety as a topological space or just merely underlying set, and a morphism between varieties or a continuous map or just a set map. Okay. This will hopefully become clearer as we go along today. Okay. Now, in order to define a group object in a category, that category must have finite products and a final object. Okay, so let's assume that there are finite products and final object. I will explain what these mean. So product just means in the category of sets, for example, product just means Cartesian product that we very well understand. And product in topological spaces means the usual product, underlying set product with the product topology. Okay. However, this is too loose and not good enough for our present purposes. We need to understand this better. So here is a categorical definition of product. Okay. So the definition of product by its universal. So suppose we have objects y and z. So for example, think of topological spaces, y and z. Then what is this y cross z? This topological space. What property must it have? So it comes with two maps. This I called py, which is a projection to y, and another map which we call a projection to z. So these are just continuous maps. Okay, the projection is just a name. At the moment, it is just a continuous map. Okay, and the comment is, although when we speak of a product, we only think of, we write this usually, and we don't, we suppress in the notation and while speaking both these projection maps, but they're there very much. Such that these maps are universal in the following sense. Given any object A and maps from A to Y and A to Z, there exists a unique map from A to Y cross Z such that these things hold. So let me draw a picture here. That will become clear. Let me see what I should choose, what color I should choose. Maybe this color is good. Okay, so let's draw a picture here. There is there is a Y, there is a Z, okay, and there is Y cross Z. So there are projection maps here. Okay.
Raghavan, this is not visible, at least on my screen. Sorry. Yeah, now it's coming up. Now it's coming up.
So if I have a map A, right? Sorry, if I have an object A and maps here, right? Then there exists a unique map here. It's important that it is unique. There exists a unique map. This is important. Unique map here. So this is SY, this is SZ, and this is S, such that S followed by this projection gives me SZ, and S followed by this projection gives me SY. Okay. In other words, to give a morphism to Y cross Z from some object A is the same as giving two morphisms, one from A to Y and another from A to Z. Okay. Observe that although we have written it as Y cross Z, there is no first or second coordinate here. There's no ordering between the Y and Z. So you have this. Okay. So this is the definition of a product. And you can check that the usual product in topology that you have, the product topology on the product set, on the Cartesian product of Y and Z is defined such that precisely this universal property holds. Okay, so what is, okay, I will talk about, okay, so what is a final object? A final object in a category is an object into which there is a unique map from any given object. Right? There is a unique map from any given object. For example, in the category of sets, the singleton object is, if I take a singleton, that's a final object. In the category of topological spaces, there is a final object, namely, again, a singleton. And in the category of varieties, again, a singleton is a final object. Okay? If you want, you can take that final object in the category of varieties. In the category of varieties we are interested in to be C0, just the point. Now, what is, so I'm going to define a group object in a category which has finite product and a final object. So it's an object equipped with three maps. One is just think of this. I'm not doing anything here. I'm just jazzing up the definition, good old definition of a group. There are three axioms in a group. There is a multiplication, and that satisfies the associativity axiom. There is an inverse, and there is the identity, and there are axioms relating these three objects, these three operations. And that's all we are doing here, except that we are doing everything in terms of maps. Okay, so it's an object G along with there is this mu, there is this inverse, and there is the identity, such that. Okay, now here I take G cross G cross G. Well, you may say this is ambiguous, right? Indeed, it is. Do I mean G cross G like this, or like this? That's a question mark. But we will see very soon that it doesn't matter. I'm going to do it here in a minute. Okay, perhaps I should have done that before doing this, but anyway, I have arranged it this way. So it doesn't matter which way you put the bracket. Okay, you get the same object. So up to unique isomorphism. That's what it means to say I get the same object. So I can either take this as mu and then this as identity, right? Now, we have to be very careful here. Although you can think at the level of sets, we are not strictly allowed to do that. You should think of these as maps according to this. So which means to give a map into G cross G, you must give me a map into G and another map into G, right? So what is this mu map into G? So that map is G cross G cross G to this projection. So here I think of this as a product of G cross G with G. And so there is a projection to G cross G. And then there is a and then there is mu from G cross G to G. So that gives me a map mu into the first coordinate G. There is also a projection to the this third thing here G, and then I take that composed with the identity map to G, and that's how I get a map to this one from this triple product. And so by the universal property, once I give a map to this and once I give a map to this, there is a map to the product. Okay, so that's how I think of this. And similarly, here this map is doing it the other way. G, you do the G cross G first and the G next. Okay, and so that's what these things mean. And this is the associativity axiom, right? This is you first multiply these and then take the product and multiply with the last thing. Here I'm doing it the other way. This way, when I go, I'm doing it the other way. That these two must give me the same map. This means that whether I go like this or go like this, I get the same answer. Okay, and the identity map, you think of it as a map from the final object to G. Because there is a point in G, it identifies a certain point in G, right? And so there is this. This gives you the identity. So you will write one. We'll write G is equal to 1 times G is equal to G times 1. That is what this is, right? And this is just G inverse G is equal to G inverse is equal to 1. Okay? So let me not belabor the point. I think this is clear enough now. Okay? One more point here, that this universal property defines this object unique up to unique isomorphism. So let us, for example, use this. So let's illustrate what I mean by this to show that these two are isomorphic, right? Whether I do x cross y to z, and in fact those are equivalent to this. Okay, how do we do this? For example, what does this mean? So you have x cross y cross z. To P X cross Y. Well, it's getting a little messy here. Let's see how I'm doing on time and see if I want to do this at all. Okay, I've spent about 15 minutes, so maybe I'll leave this as a pleasant exercise for you to do. The space I've left for myself may not be enough, and if there are any questions about this, I can go on in some more detail, but perhaps this is something that we all understand very much. So unless there is a question, I want to move on.
I have a question. So,
Sure.
So how do we exactly define X cross Y cross Z?
So it is the object where you have maps to Px, Py, Pz.
Oh, thank you.
Yeah. And with the appropriate universal property. Okay, good. Thank you. Yeah, this is good. If you have any questions, I probably am belaboring points that are obvious.
Yeah, I have one question.
Sure.
Can you please explain that diagram identity singleton, that second diagram, G to G cross G, you have map 1 cross ID.
No, this one or this one? This one, right. Okay.
This
so
identity.
Okay, so this, that's why I wrote this here, right? So one is a map from, so there is, you can similarly prove that G is actually isomorphic to, you can write it as this final object cross G. So if I cross it like this, if I take the product, that's actually isomorphic naturally to G. So this G I can think of as star cross G, and then I can take 1 cross ID, because 1 is a map from star to G and ID is a map from G to G. Does that, hopefully that explains it.
Yes.
Okay, good. And similarly on this side, I do this.
Yes.
Okay. Any other questions? Yeah, and by the way, this statement is true except if it exists, right? This, whatever you define by the universal property, if it exists, it is unique up to unique isomorphism, but it may not exist. Okay, for us, products do exist. Okay, so let's do some examples. What are group objects in sets? They are precisely groups as we know them, right? So although this fancy definition reduces the usual definition of groups. Okay?
So what do you mean by
Sorry?
Sorry, I have a question. Like, what do you mean by
Sure.
So
I'm not, you're not audible. Hello?
Hello, 1 second.
So his question is, what do you mean by if it exists?
There may not be an object with this property. They may, so I can define, this product may not exist in certain categories.
Yeah, he's happy with the answer.
He's happy with the answer. Okay, good. Yeah. In general, I mean, not just the product, most things like tensor product, you name it, direct sum. I mean, universal property is a very common thing in mathematics. And whenever you define anything by a universal property, it is always unique up to unique isomorphism, but it may not exist. Okay, let's look at examples. Group objects in sets are precisely groups. Group objects in in the category of topological spaces are called topological groups. Okay, what this means is that there is a map here, which is G cross G to G, which this is a continuous map. and there is an inverse map which is also continuous from G to G, and there is an element of G which plays the role of the identity, and these satisfy these axioms. Right. So, in other words, there is a group structure, there is a topology structure, and the two are compatible in the sense that the multiplication and the inverse map are continuous maps. Examples are GL and C, right? I'm now thinking of the usual topology, SL and C, usual topology, and M and C. These are matrix multiplication, this matrix addition. These are all topological groups. Okay. So now, to recall, we wanted to define algebraic group, and we have defined it as a group object in the category of varieties, and hopefully we understand what it means for something to be a group object. That's what we spent the last 15 minutes over. But what do we mean by in the category of varieties? So what is this category of varieties? Okay. So here is perhaps the most important thing I want to say today. The precise definition of this will take a while. Okay, so this notion of variety, although this is very basic to what we are doing, is something that we are not going to define for a while fully. Okay, it's kind of just to give you an example. It's like how a child, for example, learns to know what a dog is, right? You will never give it. I guess none of us ever had a definition of a dog, right? But we understood all of us understand what a dog is by just seeing enough examples of dogs. So that's kind of similar to what's going to happen. What we will do is say this, for example, is a dog. So that's the kind. This is a dog and this is not a dog, etc. And we'll make enough statements like that, and finally, hopefully, we know what a dog is and when we see it. Right? Okay, but we can say a few things for now. Whatever a variety is, it has the following attributes. Like a dog has 4 legs. Unless it's lame or something, right? And it's a canine or something. It has some attributes. It has an underlying set, and that this is some technical thing of this. If you've seen this, then you know what it is. But if you don't, then just take it as that the underlying set is called the underlying set of closed points. Just take this as terminology. Okay. There is a topology. This is what I was mentioning earlier. There is a hierarchy. So the variety, there is an underlying set, and there is an underlying topological space. The topology on this set is called the Zariski topology. Okay, and furthermore, there is a ring of functions, and that's called the ring of regular functions. These functions are called regular functions. So let us look at some examples. So, like I said, now we are going to. I'm going to tell you, without giving you the definition of a variety, I'm going to give you some examples of varieties, and let us look at these attributes in each case. So we've seen this definition, right? Affine algebraic variety, maybe affine algebraic set is what Krishna called it. It's the same thing. It's the loci of it's the zero locus of a set of polynomials over some index set in n variables. So you take a bunch of polynomials in variables, doesn't matter whether it's finite or infinite, and look at the common zeros of them. I call that X, right? That is an affine algebraic set or an affine algebraic variety. What is the underlying set? It is the underlying subset of Cn, which is the locus of zero. Simple enough. What is the topology? Well, on Cn, we saw there is a Zariski topology in which such sets, X, are the closed sets, right? And so this is the subspace topology on X, right? And what are the regular functions? The regular functions are precisely, the ring of regular functions on X is precisely C, X1, Xn is the ideal generator for these. Okay, maybe I should take radical of it. That is, you take all the functions that vanish on X. That's a better definition, but by Hilbert-Knudsen answer that we saw last time, that is equal to the radical of this string. Okay? And that happens only if the field is algebraically closed. So it's important that I take C here. The more correct way to do it is just take the equations that vanish on X. That set may be larger than this set. Now let's look at some other examples. N cross N matrices of determinant 1. Right? Now the determinant equal to 1 is a polynomial, is a condition. Therefore, this is the underlying set is SLNC. The topology is again the Zariski topology on Cn square restricted to this, and this is the ring of functions. And to take a more simpler example, this should be y is equal to x square. Right? So the parabola y equal to x square. We all understand from high school what this set is. It has a Zariski topology, and this is the ring of functions. Okay. Now, okay, here is something that's probably new that we didn't see last time, maybe. So, how do I define product of two varieties? As we have seen above, this product is a very important thing for defining algebraic groups, a group object in the category of varieties. So here is how to construct the product. Okay? So if y is a subset of Cm, z is a subset of Cn. These are now varieties, affine algebraic varieties. Observe the following. I am now just doing everything for affine algebraic varieties. This category of varieties, in fact, will be much larger. If you remember, Krishna started defining what are called projective varieties at the end of his talk. But as I said, we will not worry about giving a precise definition, but rather, as we go along, expand our horizons. Right? So this is just to know how the product works on affine algebraic varieties. So y is defined by a set of equations fi, and z is defined by a set of equations gj. So I've chosen m variables here because of this m. I've chosen n variables here because of this n. Then this product y cross z, it's actually quite easy. It's what you would do if you were asked to do it naively. So it sits in the product of Cm cross Cn, right? Okay, it's that. So you can think of this as Cm plus n in m plus 1 variables, right? And it is the loci of solutions of the fi and gj. Just take the fi physically. Imagine the fi's are the variables in the yi's, but I can think of them as polynomials in both the yi's and the zj's, and except that the zj's don't appear in the fi's and the yi's don't appear in the gj's. That's all. And then I take this to be the zero locus of these two. That's precisely as a set. Just this, it's a very nice exercise, maybe immediate to see that this is actually as a set. This is just a Cartesian product sitting inside this product, and here is its ring of functions. Okay, you take the polynomial ring in both sets of variables and go modulo the ideal generated by O. Okay, again, I am loose here. I should take the radical here. Okay, unless I say, when I say by the vanishing of fi, I mean the ideal of those vanishing on y is generated by fi. If I take that, then it's okay without putting the radical. Okay. Okay, but here's a caveat. So the underlying, okay, let's form the product in the category of varieties. So this is the product. And as we have seen here, the underlying set of the product is the product of the underlying sets. So I hope that is clear. That's just from this construction. However, observe that the topology on this product is not at all the product topology. Okay, here, the topology on y cross z is not the product topology. For example, you can take the product C cross C to be C square. Now, this is given its Zariski topology. Okay? This y cross z is given not the product topology, but the Zariski topology here. And the Zariski topology on C square is not the product of the Zariski topologies. This is something very nice for you to figure out which is finer, etc. So let me not, this is something you would, if it is not already familiar, then you would do well to spend some time on. Okay. So much for objects that are varieties. Let's talk a bit about morphisms between varieties. So here, let me again just restrict myself for the moment to affine algebraic varieties. And let's say we have X is contained in Cm. Sorry, let me use Y and Z because that's what I use there. Let me use this. C, same notation as before. Here, Z is contained in Yn. Okay. What do I mean by a morphism from Y to Z? That's what we want to understand. Sorry, this is C. Okay. Now, let us first understand what is a morphism from Cm to Cm. Let us take the special case when Y equals Cm and Z equals Cm. Okay. Then it is easy to define what this is. So here, what I do is you look at these coordinates, right? These are the Z coordinates here, Z1, Z2, Zn, right? Now, if I have a map here, F, and these coordinates are Y1, Ym, then each of these Zi is a, if I look at this, right? So if I look at F and then compose with the function Zi, I'll get some function on Cm, right? This must be a polynomial, is a polynomial in the Y's for every, okay, let me use J here, 1 less than J less than N. That's what it means. So what it means is I look at the projections to each of these N coordinates, right? Each of them must be a polynomial in the, it's a function to complex numbers. That must be a polynomial in the Yi's. That's all I'm saying. Okay, right? And so what is a morphism? Okay, we are done with the definition in the special case. Now let's go to the general case. I want to define a morphism from Y to Z. How am I going to define it? I'm just going to say morphisms from Y are just restrictions of morphisms from Cm. So the only morphisms that are allowed on Y are those that are morphisms from Cm. So for something to be a morphism from Y to Cn or Y to Z, it must be actually a morphism from Cm. It must be the restriction of a morphism from Cm. Morphisms to Z are those which have images in Z. That's simple enough. Okay. So now we have the general definition. Y to Z just means it must be the restriction of a morphism between Cm and Cn to Y and must have image in Z. That's all it means. Okay. Now, here are some attributes of morphisms. Okay. There is an underlying map of sets. The underlying, so these are topological spaces. Remember, they have the Zariski topologies. And if I just look at that map at the level of topological spaces, it's a continuous map. Okay. Moreover, you have this Y to Z, if you have a morphism. Then you have a set of functions here, the regular functions on. So there are a bunch of complex valued functions on Z, which we have decided to call regular functions, right? I mean, these, remember, are just for Z, it would be C, Z1, Z2, Zn divided by the ideal of Z. And similarly for Y. So when I have a map like this, I get a pullback on functions. So if I pull back a regular function, this is called an element of this is called a regular function. I get a function on for Y, but that must land in the regular functions of Y. In other words, regular functions must pull back to regular function. Right? By pulling back, by just composing it with this map, any function on Z becomes a function on Y. What we are saying is, if the function on Z that I choose is regular, then the pullback, its pullback to Y by means of this map must also be regular. Okay? Okay. Maybe this is a good point to ask again if there are any questions. Okay.
So,
maybe, yeah.
So I have, so this regular, so ring of functions. So when you quotient it by the radical, so I have multiple ideals and we have different radicals. So the ring of, so it is rings of function or just one ring of function?
It is ring of functions. It is. So, okay, let me clarify that. When I say ring of functions, it is, okay, it is C. So, okay, let me define this clearly. Suppose I have Y sitting inside CM. Okay. And then remember, Krishna defined I of Y.
Yes, yes.
Yes. So this is uniquely defined.
Right.
And this is a radical idea. And so this ring of, it is this x1, sorry, y1 to ym. Is this clear?
Yes. So,
yeah. So it is uniquely defined. There is no ambiguity. It is a, for example, it's a reduced string.
Okay, so,
meaning it has no nilpotents.
Okay, thanks.
Yeah. Okay. Good. Any other questions?
If I may ask a question about what you mentioned, that the topology of the variety y, x, z is not a product topology. So
yeah,
this would explain things we saw last time, for example, where we had a set that was open in A1 or C, and then we had the set, the same set was closed in A2.
I am not sure. Perhaps somebody else in the audience can answer that question. I don't see the connection between this and that, though.
So I have written something to that question in the chat. Perhaps you can read it.
Aha. Okay. Sorry, I cannot read the chat as I'm.
No, it's fine. I mean, I have.
I saw the answer. Thank you.
Okay, good. At the end of the talk, I also would like to know the answer, Krishna. What answer you gave?
Okay.
Yeah. Okay, so let's look at this example Krishna gave once again. So this is an example of a, okay, this is not, I mean, sorry for having not given myself room. I wrote it here under this, this. I'm going to just think of this here. So let us do this example of a morphism that is bijective, but the inverse is not a morphism. Okay, so here, so let's think of this as C. This I'm drawing it vertically, and T. Although this is just a real line, I mean, this is typical. We draw things in R, I mean, and then think in C, etc. Okay, so let us take this map. So this is the map to C square, I think Krishna had this map, T squared, T cubed, right? And so the image looks like the following. Let me show different color here. So since I'm drawing the real picture, T square, this is always positive. So I should lie or non-negative. So to the right side. So it looks something like this. Okay. Now, if you look at this definition, this is a perfectly good morphism, because when I project to the first coordinate, I get T square, which is an honest polynomial on C. Right? And if I project to the second coordinate, I get T cubed, which is honest polynomial on C again. However, suppose I want to take this is a bijection also, no problem. As you can see from this picture, only 0 goes to this origin. Right? However, if I want to take the reverse map, you would have to do, so let me do it in red. You would have to, T is equal to, you would have to write T cubed by T square, or if I call this was X and this is Y, I call it Y by X. Now you see, Y by X is not what should be a regular map. What are allowed morphisms here from this? They are just morphisms. There should be restrictions of morphisms from the affine space, which is just K, X, Y. Y by X is not there. Okay. I mean, this is not a proof that you cannot write it in some other way, but there you go. I mean, at least it's believable. Okay. Okay. That finishes one part of the definition. So what we have done is defined an algebraic group. It's a group object in the category of varieties, and we have defined some, or we have looked at certain attributes of varieties and morphisms between them. Okay. Now let's talk about action of an algebraic group on a variety. Okay, so it is defined as follows. So now this is a group object. Okay, I should have given maybe some examples of this. The examples are here coming just in a little while, so bear with me, please. So let's take a group object in the category of varieties. In other words, an algebraic group G and a variety X. A morphism G cross X to X, right? This must be a morphism of varieties. Now, what do I mean by this? G cross X, this is the product construction that we have just seen, right? So for example, if G and X are both affine, we now know what this is, right? We have a very good idea in the previous slide here, right here, what that object is. Which at the level of points. So I can take this, and this is a morphism of varieties, and we saw that there is a hierarchy. We can just go to the level of topological spaces, or even to the level of points, meaning closed points. And so I get a map. And so I get a map from G cross X to X. The notation is the same, but at the level of points, I mean G, now I think of it as the underlying set of G, X as the underlying set of X, and this makes sense because the underlying set of the product G cross X is the product of the underlying sets. So it makes sense. Okay, so which at the level of points defines an action. So this is the usual definition of a group acting on a set, right? With which all of us are familiar. Here are the axioms, right? And of course, this holds for all G, H, X, and so on, which I'm not written. So what are examples? G on itself in multiple ways: left, right, conjugation, maybe even twisted conjugation, etc. Okay. Now, basically anything that you can write naturally, with objects like GLN, etc. The condition that it is a morphism is going to be very naturally satisfied. Okay. So for example, here, what this means is you take the G cross G to G. There is a map. right? Now, what is that map? That is it's a group object in the category of varieties. Therefore, this is the multiplication map. I am claiming that multiplication map satisfies this property. Okay, that's obvious. So that is the left action of the unit set. And similarly, just like you have for ordinary sets, you can define right action, conjugation, twisting conjugation, etc. Okay. Now let's come to affine algebraic group. Okay. So what is this? I'm going to define it in a moment, but let me pause here to say that these are the same as what are called linear algebraic groups. The more common term is linear algebraic groups, not affine algebraic groups, for traditional reasons. And we will later on define what this means and show that in fact linear algebraic groups are affine algebraic groups almost by definition, and we will show that every affine algebraic group is actually a linear algebraic group. Okay? So these two notions, they are a priori different, will turn out to be the same. So what is this? An algebraic group, which means a group object in the category of varieties whose underlying variety is affine, meaning it's an affine algebraic variety. Either that, or you can alternatively say that instead of looking at the set of the category of all varieties, I just look at the category of affine algebraic varieties, and then it is a group object in that. You could do it this way or this way, and it would be the same. Okay, now let's come to the examples. So Cn as a vector space addition. So here I mean Cn with the addition structure is an algebraic group. SLV, so you take a vector space over C of the finite dimension, and then look at linear transformations of determinant 1, which after you choose a basis, you can identify with SLNC, I should write. Oh, okay, I meant to say, okay, this is contained in, sorry, not equal, contained in Cn square when n is dimensional. Now, what is let's look at the other attributes. So these are the attributes that are the underlying sets. The other attribute was topological spaces. That's the Zariski topology. We understand that now well. Now, what are the rings of functions? This is just a polynomial ring. What's the ring of functions here? Is the polynomial ring in n square variables, determinant -1. Now, here, Krishna did this, but since maybe it was a little too quick, I'll recall this for you. If f is a non-constant polynomial in n variables, okay, then df, which is the points in Cn where f does not vanish, which is a Z open set, is considered an affine variety by the following identification. So for example, if you look at GLN, right, that is defined like this, where n is n square, and this d of the f is the determinant, right? GLN is precisely those n by n matrices with non-zero determinant. Okay, how do I make that's an open set in this Cn square, right? Here, if this is an open set in here, how do I consider it as an affine variety? It is through the following identification. So you consider one more, you add one more, give yourself more room, add one more ambient space. So that's y. These x's are the variables corresponding to the Cn. Okay. Now, if I look at this equation here, fx y is equal to 1, and then the points, the solutions, the loci of solutions of this equation in Cn plus 1 are in bijection with those of the non-vanishing of, they are in bijection with df by forgetting the coordinate y. Y I can recover as 1 by f. Okay, so I can forget y and it doesn't make a difference. So by this identification, I think of this as an affine algebraic variety. Although to begin with, it looks, it's only an open set. And what is the ring of functions? it is, of course, I'm using this to know it as an algebraic variety. So I must take these many variables, x comma y, and this is the equation, right? Of course, this is I'm claiming this is the this is all the this, meaning this is also its own radical. Maybe that takes some proof, but that's this, but that is precisely this. Okay? For example, you can see that this is a prime ideal because this is this is a domain. Okay, so that's a proof that this is a radical ideal. So it is isomorphic to the ring, the variables x adjoined 1 over f. For example, for GLN, it will be n square variables and 1 over determinant. So the 1 over determinant, although it's not a polynomial, it's still a valid regular function on GLN. So more examples. So now using this, we can do this C star n, because C star is just the non-vanishing of the variable x on this, and then I can take product if you wish. Okay? Or maybe I can do it by other means as well. Okay? Maybe I can think of Cn and non-vanishing of several of them. But anyway, so let me not belabor that point. So GLV, and you can also take abstract subgroups of GLV. Okay, and a comment about this word, use the word this abstract. When we say abstract subgroup in this, when we are talking of algebraic groups, what it means is that I am only talking about the underlying group, right? So that is usually achieved by this putting this adjective in front, abstract group. So suppose I take an abstract subgroup of GLV, meaning just a subgroup without any consideration of variety. But if they are defined by vanishing of regular functions, then such a thing is also naturally now an affine algebraic group, because it's going to be a closed set in here, and therefore it is going to be a closed set in this bigger thing where GLV is embedded, and therefore it has the structure of an affine algebraic variety as well. So for example, you can take the diagonal subgroup inside GLM, right? That is defined by the vanishing of all the non-diagonal elements, or just the upper triangulars. So this is defined by the vanishing of all the lower triangular, strictly lower triangular alternates, etc. Those are examples now of affine algebraic groups. Now let us come to actions, right? That's what we started doing. Okay. So here is an action which is very natural. In fact, it is the defining action. So GLV cross V to V, right? Where V is this vector space, finite dimensional. Okay? And this is a linear map. Okay? Now, this is a morphism you can easily check, because if I take this, by the given condition that each of the projections must be a valid regular function on this product. That is the condition for this to be a morphism, and you can check that very easily. Okay, so this is and V to GV is a linear map of V. Now, there are actions of G on varieties, and there are actions that are called representations. So what is a representation? If I take a vector space, consider it as a variety, and then, okay, let me say it this way. If I take a vector space and an action of GLV on linear action of GLV on that vector space, such that this map, GLV cross V to V, the resulting map, is a morphism, such a thing is called a representation. Or you can, just like we do for finite groups, what is a linear representation? It's either an action on a vector space V such that each G acts linearly. That's one definition. The other definition would be that you have a homomorphism, group homomorphism from G to GLV. Right? We have that other definition here as well. So maybe we'll take this definition as our official definition. So a representation is a map from G to GLV. And now we want this map to be group homomorphism for it to be called a representation. But for it to be a representation of algebraic groups, we want this to also be a morphism of varieties. Okay, so that's what I've said here. It's a morphism such that at the level of points, it's a group homomorphism. Okay. Now I want to talk about certain properties of algebraic groups. So let me recall something about irreducibility. Krishna defined this, but let me very quickly recall for you. Okay. So here is a point to keep in mind. Points in a variety typically display different algebra geometric behavior. So suppose I take an algebraic variety, in other words, the loci of zeros of some set of polynomials. I look at points on them, on this variety, then different points will have different properties. For example, here is a simple example. You look at this xy equal to 0 in C2, right? Of course, the picture is drawn in R2. The loci of zeros is two straight lines, the x and y axis intersecting like here. Now, notice that there is something strange about this point here. This lies in, this will be an irreducible component, and this will be an irreducible component. And while all other points lie in a unique irreducible component, this point lies in two irreducible components as opposed to other points. So since you may not, I mean, perhaps you're familiar with irreducible components, let me remind you of that. This paragraph here is to just remind you of that. So very quickly, a subset X of a topological space is irreducible. In particular, a topological space itself is irreducible. That is included here in this definition. If the following condition holds. If C and D are closed subsets and X is contained in their union, then X must be contained in one of them. Right? So it can never be contained in the union of two closed sets without being contained in one of them. Facts about irreducible. Clearly, if you remember the definition of connected, irreducible is much stronger than being connected. Okay, irreducible implies connected. Singletons are irreducible, obvious. Closure of an irreducible set is irreducible, that's an easy exercise. Continuous image of irreducible sets are irreducible, again easy exercise. Any two non-empty open sets of an irreducible space must meet non-trivially. This is also a very easy exercise. If this is not the case, then you can immediately derive a contradiction to this by taking the complements of these two open sets. Okay? And that is equivalent to saying non-empty open sets of an irreducible space are dense. Okay. So let X be a variety. This is an important fact. There are finitely many maximal irreducible subsets of X. And these are closed. Why are these closed? That is because of this. If such a thing is not closed, I can take its closure, and that would be irreducible by this closure of an irreducible set is irreducible. So they are forced to be closed, and they cover X. Okay. I suppose Krishna will be doing this, or anyway, this is very basic things about varieties. Okay, these maximal irreducible closed subsets are the irreducible components. So for example, here, these two here, this line here and this line here are the irreducible components. Every point other than the origin is contained in a unique irreducible component, whereas the origin is contained in two irreducible components, both the irreducible components. Okay. Now, Okay, now, so the most remarkable property perhaps, and the most obviously remarkable property of algebraic groups is this homogeneity. Every point of an algebraic group displays the same algebro-geometric, hence topological behavior. Okay. So for example, the property, the thing that we just saw, if this picture cannot be the underlying topology of a algebraic group, because every point has the same algebra geometric behavior, which means you cannot have a point that is contained in lies into irreducible components. Okay? That's what it means. More generally, if you have any variety on which an algebraic group acts morphically, that's just another way of saying it. G cross X to X is a morphism of varieties. And transitively, this is in the usual set, underlying set theoretic sense. Then every point on X on this variety has the same algebra geometric properties. Okay? And why is that? The reason is very simple. Okay? It is because every G, this map G X to X is an isomorphism. First of all, it is a morphism because G cross X to X is a morphism. Okay? And you restrict it a morphism to this, you restrict this G cross X to X is a morphism, and this, you take this here, this is isomorphic to X, and you take it as inclusion here and compose. That's what what is meant by this. This is an isomorphism because there is an inverse morphism, namely putting G inverse there. G inverse would be its inverse. Okay, so if the action on X is transitive, given X here and X1, some other set, I can find a G which is an isomorphism which map X to X1. Therefore, X and X1 must have the same geometric properties. Okay. So, example of this, of the usage of this. Okay. So here is the statement: a connected algebraic group is irreducible. So look at this example here. This is connected. This set is connected, but it's not irreducible. It is the union of this line and this line, which are proper closed sets, right? So this is connected but not irreducible. But I'm saying if an algebraic group is connected, then it has to be irreducible. Okay? Here is a proof. It's a very pleasant proof. Suppose there is more than one irreducible component. Okay, if not, then you're done, right? Okay. Suppose there is more than one irreducible. If no two of them intersect, you would get a disconnection, right? You have several components and they look like this. And you would get a disconnection, and we are assuming the group is connected. Okay. Now, you are done. So two of them should intersect. So suppose X and Y these are components of this group, and they intersect, right? Then a point in the intersection like this here is contained in more than one irreducible component. It's contained in X and it's contained in Y. But there is also a point contained in precisely one component. Namely, take this component X and subtract the union of, take away this set minus of all the union of the other components. The fact that this is an irreducible component means that it is not contained in the union of these. So this is a non-empty set. And therefore, any point here is contained in a unique irreducible component. So this point is contained in two of them at least, and a point here in X that does not belong to any of the others is contained in only X, which cannot be, because I can map this point to this point by means of an isomorphism, right? By a translation by a group element, which is an isomorphism, right? That's it. Okay, so okay, so what this means, so let me be, I leave this as a pleasant exercise. So there are finitely many irreducible components. That's true for any variety of an algebraic group. No two of them intersect. So the picture is actually like this. So this is how, if I may draw a picture, this is how an algebraic group looks. The underlying variety of an algebraic group looks. And one of them, so here is the identity element, 1, right? The identity component means the unique irreducible component containing the identity. And the claim is that's a normal subgroup. The set of points here is a normal subgroup of this group, right? And it is of finite index. So each of these are cosets of this group. Okay? This is a very pleasant exercise, and I recommend highly that you do this. Okay. Okay. Any questions? I have about 10 minutes more, I think. So. Okay, let's move on then. Anyway, we have question time also, I guess. So we are close to it already. So a comment on the dimension of a variety. So it is the maximum length of a chain of proper inclusions of irreducible closed sets. Okay, what this means is, to find the dimension of a variety, what I must do is look at irreducible closed sets. So something like x0, x1. These are proper inclusions. Not of proper, I mean, the last one can be the whole set, right? So look at all such things. Okay, this may or may not be all of x. If x is irreducible, then it will be x. Otherwise, it will be some xn. N is called the length. We start with 0. Okay, so the maximum length possible of a chain of proper inclusions of irreducible closed sets is called the dimension. For example, here, for example, here it would be just a point, and then this line, for example, one of these lines. So the dimension of this thing is 1. And this is one among several possible definitions, equivalent definitions of the variety. For example, you can define it using not the ring of functions, because although they are well behaved for affine algebraic varieties, they are not so well behaved for, say, projective algebraic varieties. But you can define what are called rational functions and so on. But anyway, that I think Krishna is going to do. There are other equivalent definitions of varieties. Okay. So a corollary of this is that if you have an irreducible variety, a proper closed set has smaller dimension. Right? And one thing here is that if you have a variety, then this length has to be finite. It can't be infinite. That's one of the restrictions on a variety. The underlying topological space is what is called a Noetherian topological space. And that, okay. Now let us come to an important theorem. First basic theorem about actions of algebraic groups on varieties. Suppose that an algebraic group G acts on a variety X. Let Y be the closure of an orbit of G, which I indicate like this, Gx. This is X, not a cross. Then Y is irreducible if G is connected. Okay, let's look at the proof of this. Okay, if G is connected, then it is irreducible. So Gx is the image of a continuous map. So that is irreducible. And Y is the closure of an irreducible set. So it's irreducible. So this is okay. That's all there is to this. Okay. Basically, what I'm saying is many of the things here, this proposition here follows from what we have done before already, but it has some additional inputs which we have done, which these are good to take as black boxes. I'll come to them, these facts that are mentioned here. Gx is open in Y. How do I see this? Okay, let us look at this comment. So let's assume that G is actually connected or equivalently reducible. So here it is not a hypothesis. What I'm saying is, let us just do it in that case, and the general case follows, and it's left as a nice exercise for you to finish using these ideas. Okay, so to go from this special case to the general case is already something that we know how to do. Okay, but there are things that we haven't seen until now for the special case. So let us concentrate on the special case. Okay, now I am claiming that Gx, this orbit, is open in its closure Y. Y is its closure. Okay. So here is a fact. Okay, this is a theorem due to Chevalley, and there was Chevalley's theorem was mentioned in the title of topics that I'm supposed to cover. So this is what it refers to. Okay. The image of a morphism contains a non-empty open subset of its closure. This is the statement. Okay, so what that gives us is that Gx is the image of a morphism. It is the image of a morphism from G to X, where little g, it's the image of this morphism. G to X, where G goes to Gx. Right, X is fixed. Remember, X is fixed. Right? So this is a morphism, and what this gives us is that Gx, which is contained in its closure, and this is Y, this contains an open subset of Y. What I want to claim now is that this itself is open. How do I manage that? Well, that comes from homogeneity. Right? If I have a point here that has an open subset, open set in Y contained entirely in Gx, right? I just move that around inside Gx, right? I act by G. Notice that G fixes Y because Y is just the closure of this. So G fixes this, therefore G fixes Y, etc. So this follows from this fact. At a first pass, it's good to just take this, accept this fact at face value and not worry about its proof. Because I don't think we will, the kind of things that we are going to do from now on will ever get to the, ever involve, if I'm not mistaken, looking under the hood of this machine. So it's no harm, I think, in just accept this fact and learn how to use it. And here is the use of it. Okay. Now, Y contains a closed orbit of G. Now, this is the closed orbit theorem. Okay. So, I'm claiming Y one of the orbits inside Y. Y is a union of orbits, that's obvious. And one of those orbits is actually closed. How do I show this? Well, the complement has smaller dimension. This is a closed set. This is a closed set. And Y, I'm assuming G is irreducible. So Gx is irreducible and Y is irreducible, as we have seen in 1. And this is a proper closed set of Y. And look at this corollary. A proper closed set of an irreducible variety has smaller dimension. So this has smaller dimension. Okay? And on which G acts. So choose an orbit in this, in what I mean is Y minus Gx. Okay? And keep going. You replace X by Y minus Gx and keep going. So eventually, because these dimensions keep falling, you will see that at one point, this complement must be empty. And therefore, there you go. At that stage, you will get a closed orbit. And finally, I'll finish with this. I'm sorry, I'm already 1 or 2 minutes over time. Y is also the usual closure of Gx. And I'm not going to say much more than just say that it follows from the following statement. Suppose we have, this is something I wrote, but it's not needed. Zariski open set U of a Zariski closed set in Cn. Then the usual closure of U, okay, which could technically be smaller than the Zariski closure, actually equals the Zariski closure. So this is a very nice fact. Again, this is one of those things where it's good to put this as a black box, just accept it. And in this case, maybe I'm not even going to tell you how to prove this from this. Let us just learn to use this statement. Okay. Now, I wanted to do some examples and another theorem, but maybe this is a good place to stop. Anyway, I need to stop because I'm over time. Thank you.
Oh, yeah.
Samples. Sorry. I mean, I don't want to start lecturing again. I hope this is okay.
Yeah.
Since I take it as the answer to your question. Okay.
Yeah.
So GLN acts on Mn by left multiplication, right? Then what are the orbits? They are determined by what we call row reduced echelon forms. Okay, so this here is a good recollection of some of the linear algebra that we all understand. The zero matrix forms a closed orbital. So look at GLN acting on Mn by conjugation. Then, as we know, the orbits are indexed by Jordan canonical forms. That's why we study Jordan canonical forms. There is a unique, in every similarity class of matrices, there is a unique matrix in Jordan canonical form. That's the content of this statement. Now, scalar matrices obviously form singleton orbits, and hence they are closed, right? Because Gx G inverse is equal to X if X is a scalar matrix, because they commute with all matrices. Now, here is something interesting. The orbit of any matrix M with distinct eigenvalues is also closed. This is a very nice exercise. And here is the very quick proof. Because N belongs to the matrix N belongs to this orbit if and only if it has the same characteristic polynomial as M. Okay, so I claim this forms a proof of this, but maybe if you're seeing this for the first time, you do well to unwind what this means. Okay. Here is one more example. GLN cross GLN acts on Mn by this GH acting. So G and H is this group element here, which is a pair. X is this matrix in Mn, is given by Gx H inverse. A comment here is that this H inverse is just to make it a left action. Okay, not very serious, right? If you take it to be H, then in one of the axioms you'll get a slight issue. You can, if you wanted to talk about right action, then it will be all right. If you write Gxh, it will be action by this GLN on the left and this GLN on the right. Orbits are indexed by rank. There are finitely many orbits, one for each rank, 0 to n. Okay. The zero matrix is an orbit by itself, hence closed. So hopefully this answers your question.
Yes, that's
Kevin.
yes. Yeah.